Hello and welcome to my this video. The topics we are going to cover in this video are what are the types of fracture. This particular topic is very important. This particular topic is very important. And then we will see how stress element looks like, and then we will see what are the sign conventions. Then we will visualize the stress at certain section certain section of element, right? So first one is the fracture type. You must pay full attention to understand this particular topic. So the stress type is fracture type, sorry. If the material is ductile, first we will discuss about ductile material. Especially I'll select the material as mild steel, right? Now, what will happen if the material is loaded in tension like this, right? We applied load P over this material, load P in this direction. Now, the failure normally occurs of cup and cone type, like this material fail like this from here. This is the section from where material fail. Now, actually, we know that sigma y, which is the yield stress is equal to 250 megapascal, right? So this is the yield stress, but shear stress for this is approximate. Actually, it is 0.57 times sigma y. Yes, shear stress. So the material will fail in shear on shear plane. The material will fail on shear plane first if shear stress reach to this particular dimension, this particular value, right? So the shear plane, the plane of maximum shear stress in a ductile material is at 45 degrees. When we will study principal stresses at that time, I will calculate that how theta is equal to 45 degree at this theta, the shear stress is maximum. Actually, what happens if I draw the principal stress element? Let this is the element. I draw this element over there, and these are the normal loads like P, right? And this is theta. This is theta. This P is component. Let this is P theta. Now this P is broken into two parts. One is in this direction, which is along the surface. Another one is in this direction. This particular part is known as the shear stress. This particular part is known as the shear plus, which is acting on plane. Say this plane is, if I extrude it, this plane is XX plane, which is acting on this plane, right? Now, what should be the angle theta at which this tau is maximum? This is the question. At which this point is tau is maximum. Now, after calculation, we will find at 45 degree, theta value of 45 degree, this tau value is maximum. Now, the material, if loaded in tension, then material can sustain 250 megapascal without failure. But in case of shear, material will fail at 0.57 times of sigma y. It means at a very less amount of load it will fail. Now, uh, the material will fail from which point, which plane, at what angle? So the plane of maximum shear stress will fail. So this theta will be 45 degree. That is why in case of mild steel, like this, if I load it in tension like this, in tension, then at 45 degree, theta is equal to 45 degree, then the plane will slip from here in loading, right? However, if I am this is a rod, this is a shaft or something like this. I fix it from one end. Now I apply the torque over there. I apply the torque and I draw the stress element over there. If you see this now, now what will happen? Now the case is little bit tricky. Now the plane of maximum shear stress is like this, right? So if I draw the stress element over there, then you will find this will be tau xy, this will be tau xy, this will be like this will be like this, and at 45 degree from here, this will be sigma normal stress, but sigma normal will be less, right? So the plane of failure will be this one under torque. The material will fail straight from here. So with the application of load, the plane is changing. If I am applying normal loading, then it is failing at an angle like this, 45 degree, and this such kind of failure is known as cup and cone failure. However, if I apply torque, then plane of maximum shear is perpendicular to this. This is this one xx, right? However, if the material is brittle material, then the then this system will be different. This system will behave differently. We know that the brittle material like cast iron. Here I am taking an example of cast iron. If I load it in this is cast iron. Now I am talking of cast iron. I am not talking of ductile material. If I apply load P over there, then the material will fail directly from here. It will break in tension like this, right? However, if I apply same kind of torque over there, because this cast iron is more strong, this cast iron is more strong in tension and more strong in shear, more strong in shear and less strong in tension. So when load is applied in tension, then the plane is perpendicular to applied load. However, if I apply torque on a cast iron material, and if I draw the stress element will be similar, but the plane of failure will be 45 degree. Plane will be like this. So the failure will be from here like this in case of torque is applied on the material. Now this is example of brittle material, cast iron, and this is also cast iron, and this is about ductile material, mild steel, right? So this was about type of fracture under a different kind of loadings. So you must have understood this. I had also explained the concept of stress element. Let me draw it again. Before that, let me clear it. Uh, right now, what is stress element? Actually, let this is our machine element like this. This is our machine element like this, or I am applying a perpendicular load over this, a vertical load over this, torque over this. Now what will be the net effect of all these forces over my element? To simplify this or to calculate this, I draw a stress element over this element. After that, I get this stress element out of this. Now this load is acting over like this. Now it has neutral axis. This is the load, say bending moment load B, PB, and this PD, this is direct force, and this is torque. This torque is acting like this, tau xy, and this is PD plus PB. This is the maximum loading, PD plus PB, but here is neutral axis NN. So at one point these two will be plus minus. One time it will be plus, one time it will be minus, and at neutral axis it has minimum effect, right? So this is the stress element. In whole of the subject we will draw stress element most of the time to find out or to do all our calculations. Now this stress element has some sign convention. For example, if this is the stress element and this is called at positive stress element, you can remember this, that these two arrows are pointing toward each other. This is a positive stress element, and if both are coming away from one another like this, right, like this, right, then this is a negative stress element. These are the sign convention. You can choose your own sign convention also. Similarly, if load applied is getting away from the material, load is moving away from the material, then it is known as tension and it is considered positive. And if load is towards this stress element, then it is known as compression and it is considered as negative. This is another sign convention. Now visualizing a stress. If I want to visualize this, I will cut a section over there, right? Let me show simple visualization. This is a my element, stress element, and I applied a load P over there. I take a section over the element which is XX, and if I cut it, then you will see that I am assuming that these are the stresses. Like this, if load is in opposite direction, say this is my element and load is toward this, then I will cut this section. Then on this section I will show the forces like this. Although these forces are not constant near the application of load, we will see St. Venant's theory to understand this concept. Now in case of bending, let this is a beam and I applied a load P over here. Now this one is the neutral axis. Now what will happen, above this there will be tension and in below fibers there will be compression, because after bending the material will bend like this, material will bend like this, right? So the upper portion will elongate and lower portion will compress. So if I draw the cross sectional stress over this and this one is the neutral axis, then what will happen, that in this the stresses will be like this, in this area stresses will be like this, and they will pass through 0 like this. It will be like this, right? However, now this is case of bending. Now if I apply shear over this torque, now I must told one more thing, that if I apply this load there will be shear stress also. This is only the bending stress. There will be shear stress also, and shear stress will not be constant. It will vary over the section, and it will look like this. It will be maximum at center point and 0 at end points. However, if I apply torque on my stress element like this, then the stress distribution will be something like this. It will be maximum at end points and minimum at 0 point at center, like so. This is stress distribution for torque. Shear stress distribution, this is shear stress distribution, this is bending stress, this is shear stress distribution in case of beam, this is normal tension, this is normal compression. So all these are the ways to visualize the stress distribution in a machine element or in a component under observation. Thank you.